In this lecture, we shall consider the quantum theory of simple harmonic oscillator. If we draw the figure for a simple harmonic oscillator, let us suppose that a block of mass m is attached to a spring. One end of the spring and the other end of the spring is attached to a rigid support. Let us say that the mass of the block is m, and this is the equilibrium situation. Let us suppose that this is the origin. And if we consider that this horizontal surface is frictionless, and if we pull the block up to a certain extent, say up to xm, and now if we release it, then the block will execute say simple harmonic oscillation. There will be a motion, to and fro motion, back and forth. There will be some characteristics of this motion. Simple harmonic motion is denoted by SHM, and the first characteristic is the motion must be linear. Along a straight line, and second characteristic is to and fro motion. Third characteristic is periodic motion. And the fourth characteristic is the force acting on the block is directly proportional to the displacement, but oppositely directed. From the fourth characteristic of the simple harmonic motion, we have the force is directly proportional to minus x. If we put an equal sign, then it will be minus kx, where k is the proportionality constant. And known as the spring constant. Now the force is actually here is a conservative force. And for conservative force, the force can be written as the negative gradient of the potential function. And this V actually is the potential energy of the simple harmonic oscillator. We have a one-dimensional system here, the simple harmonic oscillator. Now, if we put this Fs equal to minus kx, which is equal to negative gradient of the potential energy, and from this relation we can write down V equal to half kx square. You can check it. We are now ready to write down the Schrödinger equation for the simple harmonic oscillator. And for V, we can put this 1/2 kx squared psi equal to E psi, where E is the total energy of the simple harmonic oscillator. Now we know in quantum mechanics the linear momentum operator is nothing but minus I h cut d by dx. So the Schrödinger equation can be written as this, where we have substituted k is equal to omega is equal to square root of k by m. So we square this, then we will have omega square equal to k by m, so k equal to m omega square. Now this is the total energy operator. We can actually put here operator sign, but we know from the second postulate of quantum mechanics that position and potential energies, these just the operator is equivalent to the physical observable, and also this is this. So this is the Hamiltonian operator or total energy operator. Therefore the equation can be written as this. So the H operator, the total energy operator or Hamiltonian operator, is 1 by twice m. Linear momentum operator is square plus if we make it this 1 by twice m, then it will be m square omega square x is. Take common 1 by twice m, then we'll have e square plus m square omega square x square. Remember, m is the mass of the simple harmonic oscillator. That means the mass of the block. We define two new operators. A plus, which is 1 divided by square root of 2 h cut minus I p plus m omega x, where I square equal to minus 1. And another is a minus, which is 1 divided by square root of 2 h cut m omega I p plus m omega x. And we would like to express the Hamiltonian operator of the simple harmonic oscillator in terms of these two operators, a plus and a minus. For this, let us form the product of a plus and a minus. We have which can be written as we keep these two terms, the first and the last, together, and take common I m omega of the middle two terms. And this is the commutator of x and p. And we know the commutator of x and p is I h cut. Now this is the h, we know the Hamiltonian of the simple harmonic oscillator, and this is minus 1/2, and we had here a plus a minus product. So from this we can write down h is h cut omega and a plus a minus plus 1/2. So you see the Hamiltonian operator of the simple harmonic oscillator in terms of the two new operators a plus and a minus. Similarly, we could also show that h is equal to h cut omega and a minus a plus minus 1/2. So this is another expression of the Hamiltonian operator. Now if we equate these two, equating these two, expressions of the same quantity, the Hamiltonian operator, then we get from this we can write down or this is the left hand side is nothing but the commutator of a plus and a minus, and which is equal to minus 1. So the commutator of a plus and a minus. Okay, you could also show from these two that A minus A plus, the commutator of these two is 1. Okay, now we shall study a theorem, very important theorem. Now we can write down the Schrödinger equation of the simple harmonic oscillator in terms of the operators A plus and A minus. Therefore, the Schrödinger equation of the simple harmonic oscillator can be written in terms of A plus and A minus as, so we had H psi equal to E psi is the total energy of the oscillator, and now we have H is cut omega A plus A minus plus 1/2, and also H is equal to H cut omega A minus A plus minus 1/2. So either this one or this one can be used here for the Schrödinger equation. Therefore, Schrödinger equation becomes H cut omega A plus A minus plus 1/2 psi equal to E psi, and also H cut omega A minus A plus minus 1/2 psi is equal to E psi. Okay, now the important theorem that I just mentioned few moments ago, this is a theorem, and the theorem says that if psi satisfies the Schrödinger equation, with energy E, that is A psi equal to E psi, then A plus minus psi, this will be a new state function or wave function of the oscillator, will satisfy the Schrödinger equation with energy E plus minus H cut omega, that is Schrödinger equation for this state function A plus minus psi equal to the energy E plus minus H cut omega and the state a plus minus phi. Okay, we'll have to prove this. Okay, let us consider a plus first. We have and now we use the expression for h, this one here. So we'll have h cut omega a plus a minus plus 1/2, and then here a plus psi. Now if we take this a plus inside the parenthesis, then we'll have a plus a minus a plus half a plus, and we have here psi. And now you take a plus on the left of this, so we will have a minus a plus 1/2 psi, and this can be written as h cut omega a minus a plus, and we take a minus 1/2 here, and so we'll have h cut omega. Now this is h, and this is, and take this psi inside, but this h psi equal to e psi. Now take this, now since e and h cut omega are constant, so we can bring this a plus on the left of the wave function psi. So we can write down this e plus h cut omega, and here a plus psi. Therefore similarly you can show that h of a minus psi is e minus h cut omega. Similar procedure, but in this you'll have to apply the h, not the first one, but you'll have to apply this one. Therefore we can write down a plus minus psi here is e plus minus h cut omega, and here a plus minus psi. Proved. Okay, now it can be further shown that if we operate the wave function psi again and again, then the energy of the simple harmonic oscillator will decrease by each time h cut omega and will continue. But this continuation will somewhere will end, because at a particular step the energy will be negative, and negative energy is not allowed for simple harmonic oscillator. In that case we'll have to stop earlier to the situation when we get negative energy of the oscillator. I'll show you. Okay, that means if you have this a minus square psi, then you will have e minus 2 a square omega a minus square psi. If it is cube, then 3a square omega will be subtracted from E, the energy. But this way, if you continue doing this, by operating psi by a minus again and again, your energy will decrease from E, and at a position when this energy becomes negative, and we'll have to stop just before this happens, because the negative energy is not allowed for simple harmonic oscillator. Let us suppose that the state function is psi naught, okay, where we will have to stop, and if you operate this psi naught by a minus must give you 0, because for this the energy becomes negative. This subscript 0 means we say that this state function is the ground state wave function of the simple harmonic oscillator. Now what we see here, that as we operate psi by a minus, then we go lower in energy scales. And similarly, if we operate psi by a plus, say this is jth state function, then if you operate by a plus, should give you psi j plus 1. And if you operate psi j by a minus, should give you psi j minus 1. Okay, so this one will not be just exactly equal. You will have to have a normalization constant. So is psi j plus 1 is some constant, says c j, and this is a plus psi j, and this is psi j minus 1. This is, say, d j, and this is a minus psi j. So if we write down the Schrodinger equation, let us suppose that psi naught and E naught are the wave function or state function, and energy of the simple harmonic oscillator at the lowest possible state, means we call it a ground state. Okay, then, and we would like to find this psi naught and E naught. The equation that I wrote down here, this equation would give you psi naught, because we know the operator a minus, and the energy, we can write down the Schrodinger equation for the ground state, and from there we can find out the ground state energy. So A psi naught equal to E naught psi. Now we have two expressions for H. One is H cut omega A plus A minus plus 1/2, and the other is H cut omega A minus A plus minus 1/2. Which one should we use here? We should use this one, because when we put this here, then we'll have A minus psi naught, and A minus psi naught is 0, because we cannot go down the ground state, so this will give us 0. So if we put this A plus A minus plus 1/2 psi naught E naught psi naught. So is A plus, this is A minus psi naught, this will give you 0, and this is half psi naught is equal to E naught psi naught. So is 0, half psi naught is E naught psi naught. From here, E naught is, you see, half H cut omega. So you see the ground state energy is this. Similarly, we can find out the the ground state wave function from this relation. This is equal to 0. Okay, now A minus is 1 by square root of 2 H cut omega, and this is I E plus M omega x, and this is psi naught equal to 0. So if we divide both sides by this factor, then we'll have I, and P, we know the operator, minus I d psi naught by dx minus I H cut, of course, and this is M omega x psi naught equal to 0. Here x hat equal to x from the second postulate of quantum theory. Okay, so is this H cut d psi naught by dx, and this is equal to minus M omega x psi naught. Which one can be written as this? Minus M omega x by H cut. Okay, now if you rewrite this and then we integrate it over x, this one we can write down d by dx of logarithm of psi naught, where base is e, and this is minus M omega x by integrate it. So will be ln psi naught equal to minus M omega x square by 2 H cut, and there will be a constant of integration, and let us suppose this is we write down like this, logarithm of a base e. So we bring this one on the left hand side, so we'll have logarithm ln psi naught minus ln a equal to minus M omega x square by 2 H cut. And this one gives us psi naught of x equal to a e to the power minus M omega x square by twice H cut. Okay, you see the ground state wave function, but we have a normalization constant, and this normalization constant we'll have to find out from by applying the normalization condition. Okay, the normalization condition. So we have the normalization condition. Modulus of sinus df is a one dimension and this is 1. So we substitute the value of psi naught, so we'll have a square, and this is minus infinity plus infinity to the power minus m omega square x square by h square. We had psi naught equal to a to the power minus m omega x square by 2a square. Okay, this one can be integrated by applying the gamma function. You know, we have a formula, gamma function, gamma of n is equal to 0 to infinity x to the power n minus 1 e to the power minus x dx. Well, you can apply this, and if you just would like to write down the result, then we have a formula e to the power minus beta x square dx is equal to square root of pi by beta. So if you apply this formula, or if you start by substituting a method you apply, then and ultimately you apply this gamma function, then you can obtain the normalization constant a. So this integration can be written as pi by beta. Beta is m omega square, you see, m omega square by h cut here. M omega square by h cut is beta, m omega square by h cut, so is pi h cut here, and this is square root, which is equal to 1. So is a square equal to actually is not omega square. I think it is omega. This one is just m omega x square. I'm sorry. This is m omega x square. So this is m omega x square. So is m omega by pi h cut power 1/2, and this one gives you a equal to m omega by pi h cut to the power 1/4. So you get the ground state wave function. Therefore psi naught is a into a is m omega by pi h cut to the power 1 by 4 e to the power minus m omega x square by 2 is cut, and the energy, ground state energy, we have found out is half h cut omega. So you see the ground state wave function energy we have found out. Okay, this is for today, and in the next lecture we shall find out the wave function and energy of the nth excited state, and we shall study few other topics relevant to this simple harmonic oscillator.